Today, before we begin the class, let's summarize the instruction set of the opcode that we have covered so far. So we start with root registers, which allow us to transfer data from the memory to a registers. And also we covered about the store registers that do the opposite things by transferring any value from your register back to a memory. Then we also learned about the arithmetic operation, that doing an add for a summation operation, and as well as sub for the subtraction operation, and a logical operation for AND, and as well as the logical operation for the OR operation. And lastly, we also covered about branch for branch always, and as well as we also learned about the branch that comes with a condition. So the condition could be either equal, so branch if thing is equal, or we could have branch if the thing is not equal. You could have a branch greater than, or branch less than. So at the same time, you could have a branch greater or equal, or branch less or. So of course, the way how we use branch, as what we explained in previous video, we always pair with the compare instruction. So to compare two value or two registers, if the condition of that comparison match the condition that we set, then we're going to branch to somewhere based on the label that we put. So definitely this is not the only instruction set that's given by ARM Cortex-M. So ARM Cortex-M provide more than 35 instruction set that provide additional function, which is we haven't covered yet. So I will try to introduce the rest of the instruction set slowly throughout the class. But for today's video, I would like to demonstrate how we could use simply just this few of the instruction to control the input-output of ARM Cortex-M microcontrollers. The way how ARM designed the architecture is called the memory map input-output, so that we can easily control any input or output pins by just using the load or store instruction. And the way how we control the input-output is the same way how we move data to a memory location. For this class, we were using the board built by Mbed, and they are using the ARM microcontroller designed by NXP, which is called LPC1768. So this is the microcontroller itself for LPC1768. So if you look closer, we can easily spot the port or GPIO pin that's available for this particular IC. So it starts with P, stand for port. 0 is the group of the ports. So the way how ARM group the IOs is by using a P as a port. So you have a port 0 and port 1 and port 2 for this particular ARM microcontroller. And port is just basically a groups of IOs that belongs to him. So in general, you could have about 32 IO for one particular port. For example, port 0, you could start with port 0 pin 0 up to port 0 pin 31. So same case for port 1, you could have port 1 pin 0 up to port 1 pin 31. And again, port 0.0 up to port 2 pin 31. So if you look at the microcontroller pin out, so this is the group of port 0. So you have port 0, 16, port 0, 15, 17, 18, 19, and so on. And somewhere above that you have the group of I/O that's under port 2. So port 2.9, port 2.8, port 2.7, 6, 5, and 3, and so on. So although there are quite numbers of I/O that available from the microcontroller itself due to the size that we have on the mbed module, there are only a few number of pins that actually connected to the PCB of the module that allow us to use as an input-output pin. There are few registers which is very important when dealing with the input-output. The first one is FIO set, the second one is FIO clear, and the third one is FIO pin. So the X represent the port number that we would like to use. For example, if you want to use port 0, so the register will be FIO 0 set, FIO 0 clear, and FIO 0. So as what we mentioned just now, the ARM itself is using memory map I/O. So the register that we use to control the input outputs can be accessed based on a memory address that's fixed for each register. So in this case, for example, F0 set is tied to the address 0x2009 C018. So FIO 0 clear is tied to 0x2009 C01C. And lastly, FIO 0 pin is tied to address 2009 C014. So any data that we store from register to this address will actually directly modify the status of the input-output pin. So since in this case we are dealing with digital I/O, so we could either have 1 or we could have 0. So or we call it high state or low state for any single input-output. So if you refer to the schematic of mbed LPC, there are 4 actually output LED that we can control, and the LED is connected to port 1.18, port 1.20, port 1.21, and port 1.23. So when we're dealing with port 1, as what we learned just now, there are 3 registers that we can use to control, which is FIO 1, since it is a port 1 set register, FIO 1 clear register, and FIO 1 pin register. So of course we haven't really understand what is the purpose of these 3 registers. So I will start with FIO pin. So FIO pin registers is representing the status of each I/O pins, whether it is high or low. So for example, if all the pins that under port 1 is low, so if you read whatever value you found in this location, you will get value 0, 0, 0, 0, and 0, 0. And for example, if all the pins in port 1 is high at the high state, if you try to read anything from this memory address, it will return FF, 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 FF. And of course, you will not always find all the pin is high or low. It will depend on what the devices that is connected to each I/O pin, and some I/O pin might high, some I/O pin might low, depend on the current state. So this value can be different depend on the current situation. And then for FIO1 clear registers, which in the address of 2009 and C03C, it basically a 32-bit value registers, and every bits in this FIO1 clear registers represented a I/O pins which is under port 1. This is used in case you want to make the I/O pin in port 1, either of the pin to low, so you can set the value inside FIO clear register. So this is to make the I/O pin low. That's why we have a clear there. So as you could guess, FIO1 set is the opposite of FIO1 clear, is another 32-bit register which is located at the address 2009C038. And in case you want to make any of the pins that belongs to port 1 to be high, so each of the 32-bit binary that come from this register represented each individual pin, so you can tell your microprocessor to set that pin to high based on the value you load into this register. So again, this is the register that we use in case you need to make any I/O pin to a high state. So for example, if I want to turn on the LED 1, which is located at port 1.18, so we need to make bit number 18 to 1 and put the value into the set registers. So if this is bit number 18 and this has to be 1, the rest we don't want to turn on the LED. So the value will be in hexadecimal will be, and the way why the value like that is because if you break out the hexa into the binary, 4 is in 0, 1, 0, 0 binary, and this happen to be the bit number 18. So of course you start with bit number 0 up to bit number 31st. So if I store this value 40,000 into the address of 2009C038, or which is the address for FIO1 set, so your processor or your microcontroller will go ahead and turn on LED 1 for you. So if I would like to turn on the LED 1 and LED 2, which is on the port 1.18 and port 1.20, so I need to change the value that's supposed to be written to FIO1 set. So if this case, this bit 18 and bit 20 has to be 1. So if you work out the binary and convert to hexa, basically you will get 0x0014, 00 and 00. Again, if you look at the binary itself, 4 represent 0, 1, 0, 0, and this is equivalent to bit 18 as what we learned just now. So this is bit 19, and if you extract the 1 into binary, 0, 0, 0, 1 in binary, so this happen to be bit number 20. So I'll tell my processor to turn on or to set the I/O pin at 20 and the I/O pin at 18, which is 18 and 20 as what we want, to the high state because we are using the set registers. So if you need to switch off the LED or turn the I/O pin to low instead, basically the value will be almost similar. For example, to turn off bit 18 in port 1, so the value still is 40,000. Just instead of you wrote or you store the value 40,000 into the address of FIO1 set, now we have to store this value into FIO1 clear to tell our microcontroller to clear or make the I/O pin number 18 to low. And we have learned about how to make a program to transfer data from register to a memory address in order to control our I/O by using load or store opcode. So I could have load register 0 equals to 0x 2009C038. So I wrote the address into register 0 so that I could use store based on this address. Then I also need to wrote this value that I would like to put into this memory address. So by using the same method, so load to R1, so the value is 0x0004. And lastly, I just need to transfer the value in register 1 into the memory pointed by register 0 using the store instruction from register 1 into the memory with the address given by register 0. So indirectly, I already tell my microcontroller I need to put this value 40,000 into this memory address, which is representing the FIO set. So my microcontroller, after execute the instruction, will tell the pin on port 1.18 to high and switch on our LED 1 there. So this is basically the concept of memory map I/O, how we could make use of the opcodes that we can use to manipulate the data of memory to indirectly control the GPIO based on the address which is given by the ARM itself for the set or clear or pin register. So with that, I summarize the topic for today, and we will look into more advanced example on how we could control the other I/O pins in next video.